Hi, everyone. So in this session, we will introduce central limit theorem. So using central limit theorem will allow us to use normal distribution for very important, meaningful, and important applications. So just let us introduce the idea or the theorem. So for all samples of the same size n, where n is greater than 30, the sampling distribution x bar will be approximately normal distribution with mean equal to mu and standard deviation equal to sigma divided by square root n. So, okay. So now, if the sample size is greater than n, then the distribution of this sampling mean will be approximately normal distribution. Okay. And this is really important thing. So let's see, here we have, this is the mean or sampling mean, right? And remember when we had x, if it's x has a normal distribution with the mu and standard deviation sigma. So this one will allow us to use the normal distribution. So then again, what's the central limit theorem? So basically for any data coming from any, whatever distribution, any distribution, if those sample size, if the sample size is greater than 30, then the sampling distribution will be approximately normal distribution with mean equal to mu and standard deviation equal sigma divided by n. Okay, so then what we need, so two things. So if we have a population, we said, let me write it down here. If we have a population from any distribution with mean equal to mu and standard deviation equal to sigma, and then from this population, we took a sample size n greater than 30, where this sample is simple random sample. Okay, then the sample mean or sampling distribution x bar or sampling mean will have approximately normal distribution with the mu and sigma divided by square root of n. Okay, so this is really important. So now, then what's the requirement here? We have to have one of two to use normal distribution. What we need to use a normal distribution. If the data has normal distribution, then it's clear, right? Right away, we can use normal distribution. If we don't have normal distribution, if we have the sample size greater than 30. So in those two cases, 1, 2, we can use normal distribution. If we can do so, then the sampling mean, so mu x bar, the mean of all mu. So if we have, let's say here, what we want to do, we take sample 1, and then we calculate x bar 1, sample 2, x bar 2, and so on. Imagine that till sample x bar n. And then if we take the mean of all those distributions, then the mean of all those distributions will be mu x bar. Okay, where mu x bar will equal to mu. So mu, this is a mu x bar, which is the sampling distribution of sample mean. And this is what? This is the population mean. Also, the standard deviation will be equal to this value. Sigma x bar equals sigma divided by square root of n. So now remember, so last lecture we did say if we have x, then this x has a normal distribution, mu and sigma standard deviation. Then we will use z when we make it standard, where z equal x minus x bar divided by sigma. But if we have sampling mean has an approximately normal distribution, so either this mean has a normal distribution is given, or the sample size greater than 30, then it will be approximately normal with mean equal to mu, standard deviation equal to sigma divided by square root of n. In this case, we will use z equal to x bar minus, so here, sorry, this will be mu, right? This is a mu. X bar minus mu divided by sigma x bar. And we know sigma x bar equal to what? Sigma divided by square root of n. So we can write it right away here. Sigma divided by square root of n. So remember, it's really important to know that are you dealing with a single value or individual, just one individual value, or we deal with mean of some values, right? So if we deal with just individual value, then we will use this. If we use mean of some values, then we will use this. So the other scenario, so first scenario, we have one of two, which is either we have a normal distribution or we have a sample size greater than 30. This will allow us to use a normal distribution. But if our sample not normally distributed and the sample size is less than 30, then we cannot say use normal distribution. We cannot, it cannot be approximated to by a normal distribution, okay? Then we have to use other things, which is non-parametric methods, which is, we don't have it here. So we can, so this is, we will not study this session basically, because we have to use non-parametric methods. Okay, so then for any question we will have to check our the requirement for that allowing us to use a normal distribution. So we have to check either if we have normal distribution or we have n greater than 30. So in those two cases, we can use normal distribution. So now the second thing, we have to know that if we dealing with just individual value x or mean of some values x bar. Again, I'll do it again here. If we are just dealing with one individual value or a single value, one single value of x, which is x, it will be normal distribution with mean equal to mu, standard deviation equal to sigma. And then we can use this one, z equal to x minus mu divided by sigma, okay? So this is really important if we are dealing with just individual value or we are dealing with mean of some values. Okay, then this is the first scenario. It's ready, right? So just when we study z will equal to x minus mu, which is this, divided by the standard deviation, which is sigma, which is this value. It's given. Everything will be ready for you. But here, if we have a mean of some values, x bar, might be we need some work. So if we are giving mean, then the distribution will be normally or approximated by normal distribution with the mu divided by sigma divided by square root of n. So usually in the question, they will give you mu and sigma. But to find the sigma of that x bar, you have to divide the value of sigma by square root of n. So then z, it will be x bar minus mu divided by sigma divided by square root of n. So usually you will get this value, will have it right away, and this you will have this value. Then you have to calculate sigma x bar equals sigma divided by square root of n, which is this value. So this value here. Okay, so now, yes, the mean, which is mu of the sampling distribution equal to population mean, and sigma for the sampling distribution will equal to sigma, which is the standard deviation for population, divided by the square root of sample size. Okay. Also, this value, which is sigma x bar, we also call it as standard error of the mean. Standard error of the mean. Okay. So this is standard deviation of sampling distribution or standard error of the mean. So let's take this example now. So this example, okay, let's see. So here, if you read this example, we have the maximum capacity is 4,000 pounds, which is approximately 27 passenger. And then, so the mean okay, so this is the value of mean, okay, which is, it should be, the mean passenger weight is 148, okay? So this is x bar equal to 148. Why x bar? Because they said the mean passenger of 27, which is from this sample. And then they'd say, okay, so that the 27 adults, assume that the adults may have weight that are normally distributed. So now, so we say that we can use central limit theorem if we have one of two, normal distribution or sample size greater than 30, right? But here, yes, we have normal distribution, then we can use the central limit theorem. And then we have a mu equal to 189, right? And we have a standard deviation, sigma, equal to 39 pounds. So let's see what we need to know here. The first question, they said, find the probability that one randomly selected adult male has a weight greater than 148. So now we are asking for a probability that they said greater than 148 pounds. Now here, it's important to know, are we dealing with just only single value or we are dealing with a mean of some values? One single value or mean of some values? Here in this question, they said randomly, that one randomly selected. One, that's mean what? Single, right? Single value. So since it's a single value, then our random variable will be x. So then x greater than 148, right? Remember that when we say, so now our variable, so this is unknown. So now our variable x is normally distributed with the mu, which is the value here, 189, and sigma equal to 39, or standard deviation equal to 39. Okay, so now what we want to do, I'll show you how to solve this problem in two ways. The first way, just we want to use z, right, which is, it will be probability x minus mu divided by sigma. I mean, which I should write it here, z equal to x minus mu divided by sigma when we are dealing just with only single value, greater than 148 minus mu, which is 189, right? This is the value of a mu, divided by sigma, which is, sorry. So this is the value of a mu here, 189, divided by sigma, which is 39, which is this value here. Okay. So if you calculate this, it will be probability of z, right? This value is z, greater than negative 1.05. So now if we sketch this down, it will be like this. So this is negative 1.08, and they say greater than, that's mean the area to the right. The area to the, let me write it here, to the right. So now if you want to go to use z table, it's easy. If you want to use z table, so it will be probability of z greater than negative 1.005. It will be 1 minus the probability z less than negative 1.05. Why? Because z table will give us the area to the right. So the area to the left. So if we want to find the area to the right, then it will be 1 minus the area to the left. Why? Because the area under the curve equal to 1. But if you wanna, so if you wanna use this, let me show you. If you wanna use this, then you will get those values. It will be 1 minus this value, which is 0.1469. And then when you do this one, you will get the area equal to 0.8531. Okay, so this is what you will get if you want to go use your table. But also we can remember the value now of z is this value, negative 1.05. We can go to a stat disk here, stat disk, and we write z value equal to negative 1.05, and then remember the area to the right. We say the area to the right, which is this value, 0.8531. Okay. Or also you can right away, without doing anything from the question, right away go to StatCrunch. When you sign to your StatCrunch, go to stat and then calculator, right? This is the first one, calculator, and then go to normal. Okay, And then we have the values right away. So our mean was, let me go back here to check the values. My other screen. So our mean was 189 here, 189, and the standard deviation 39, and then calculate greater than 148 compute, which is here, this is the area, okay? 0.8534, which is the shade, here, the shaded area, okay? So then this is how to find it right away using StatCrunch, or if you did use Z, you can find it from the table or the stat disk here, the area to the right, this value. Okay, let's see here the solution for this one. So now we know that we are dealing with just only single value, then we have to find the value of Z, which is negative 1.08, and this is the area. So if this is the same, this Z here equal to negative 1.05, and this is a mu equal to 0. Since we say the shaded area under the Z distribution is exactly the same as the shaded area under normal distribution. I mean normal distribution and standard normal distribution, okay? And then we got this one. If we use table, we got this one right away. And if we use the technology, I already did show you how to use it. Okay, now see the B here. Find the probability that a sample of 27 randomly selected. So now we are not dealing with only single value. Why? Because we have a sample of 27. That means now we are dealing with X bar, right? So now here they said, okay, the probability of, it's still greater than 148 bounds, but here, since we don't deal with a single value, then we are dealing with the sample. That's mean we are dealing with sample mean, okay? So they say they have a mean weight greater than 148. So this is missing. So now we know that X equal to what? Normal distribution with the mu equal 189 and sigma equal to 39, right? But now, since we will not use this, we will use this one, which is X bar. It will be normal distribution with the mu and sigma divided by square root of n. Remember, this is the value of mu, and this is the value of sigma. So now X bar, it will be normal distribution with 189, but the standard deviation will be 39 divided by square root of n, which is 27. Okay, so if we did this, we will have this value here. So our X bar will have a normal distribution, 189, and this value will be 7.51. So this is the value here. This will be 751, okay, approximately. So now, either we go right away to StatCrunch, we have here, oops, we have the value of our mean, which is the same, right? 189, but here, instead of 37, it will be 7.51, and the rest the same, right? X. So here, that's mean here, if we compute, we will get, this is the probability, 0.9999, which is basically approximately equal to 1. So now if we want to use technology right away, then this is will be 0.9999, which is approximately equal to 1. But if you want to use the z, still you can say that, okay, probability of x bar minus mu divided by sigma divided by square root of n greater than 148 minus 189, right, which is the value of mu here, divided by standard deviation, which is 7.51. So this is will be z greater than, let me see if I have it here. Yes, greater than negative negative 5.46. Okay. And again, if you want to use the table, it will be 1 minus probability of z less than negative 0.546. Okay. But if you want to use technology, you can go to stat disk. So let's say it here in the stat disk, so it'll be this one. And we have here negative 5.46, right? And if you see it here to the right, they put it right away equal to 1, which is, I mean, it's almost equal to 1. Here. Because if you see here, if I sketch down, the negative 5 something will be here, negative 5.46. And this is the shaded area, right? And we did say that the area under the curve equal to 1, which is, we almost shade everything under the curve. That's why this value approximately equal to 1. Okay, so in the other session, they said, okay, we have a normal distribution already. So we don't need to look to this one because we know n is 27, which is less than 30, right? But since we having a normal distribution, then we can use central limit theorem right away. And as the same, we use, I did say that we find the value of standard deviation of sampling mean, which is 7.51. Okay, so this is the sketch it out, and this is the value of z, right? And then it will be approximately equal to 1. So now here we say that there is 0.8534 probability that an individual male will weigh more than 148 pounds, right? And there is almost 1 probability, or do you remember if the probability equal to 1, what do you mean by that? Certain probability, right? It's, we did say if probability equal to 0, that's mean impossible event. And if probability equal to 1, then we have certain event, right? So and then there is almost 1 probability or certain probability that 27 randomly selected male will have mean weight of more than 148, right? And then this will lead us to test our hypothesis. So I believe chapter 7 will be about hypothesis test, but here just we'll take one example. If we do have some assumption, if we have or giving some assumption that probability of observed event is very small, and the observed event occurs significantly less than or significantly higher than, then what typically expect with those assumptions? We conclude, might we include those assumption is not correct. Let's say, let's see this example here. So assume that the population of human body temperature has mean, so this one, so this is assumption now, it's 98.6 Fahrenheit, okay? And assume the standard deviation also sigma equal to 0.62 Fahrenheit. Okay, and then we took a sample n equal 106 to test this one. And then they said, okay, find the probability that getting a mean of 98.2 or fewer, that's mean less than or equal. And then here, the value is, are we dealing here with the single value or a mean of some values? So clearly mean, right? Because they said the mean here. So this value will be X bar. So now we are looking for this value first. Okay, so now to find this probability of X bar less than or equal to 98.2, and we have our X bar has a normal distribution, okay, or approximately normal, because here in the question they don't mention any normal distribution, but we have sample size greater than 30. So since n is greater than 30, then still we can say that it will be approximately normal distribution with the mu 98.6, and sigma it will be what? It will be 0.62 divided by the square root of 106, right? Since we did say that sigma of X bar will be equal sigma divided by the square root of n, which is sigma. This is the value of sigma, 0.62 divided by the square root of n, which is 106. So this value, let me write it down here again. X bar will be approximately normal, 98.6 Fahrenheit, and this value it will be 0.0602197. You can use it all, or you can use just only 4 digits. Okay, so now for this value, either we can go right away to our stat crunch. Remember those two values, right? So then if we go to your stat crunch here and come here, the value of mu, it will be, oops, 98.6, all right? And our standard deviation will be 0.060297, and find the probability that less than, right here, less than or equal to, the value will be, I believe, 98.2. 98.2. So let's find this value. This is the value 1.5437 e to the negative 11, which is, if you find this value, it will be like this. It will be 0.0 10 times and then 15. It will be like this. So this is the probability. So this probability will equal to 0.0, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1, 5. This is the value. Okay, which is basically, this is basically is basically this value will be equal to, or sorry, this probability will be approximately 0, right? So this value, you can say that this is approximately 0, which is mean it's impossible to get a sampling mean equal to this value, which is here. It's impossible in this data. So this one, let me show it here. So this is the solution. So this is the sigma x bar. And then we have, this is the probability, which is, I mean, is very small. It's approximately 0 since we have z value, it will be negative 6.64. So if we go here to StatCrunch and we did write negative 6.64 and we evaluate, we will get the left equal to 0. The probability basically equal to 0, right? So now we have 0 probability here. So now we have one of those. So this is certain, sorry, it's impossible event, impossible to get the population, sorry, the sampling mean equal 98.6. This is one case, right? Or might be here, if you look here, the population mean really is 98.6, and their sample represent a chance event that extremely rare. It's I mean 0, probability of 0, right? Or the population mean is actually less than we assume. So maybe this value we did assume is not right. So this value we got from the sample the temperature of 98.2. This is from the sample of 106 people, right? But our assumption that the temperature of a human being body equal to 98.6. Okay, so it might be this one is not right. Okay, so one of those two cases. So then, because this probability very low or almost equal to 0, it's more reasonable that we conclude the population mean is lower than what we assume. We assume that the temperature of the body is 98.6. So then might be we conclude that this is not right. Maybe the temperature is closer to the sampling mean. So this is the sampling mean, right? Okay, and then the last thing here, correction for finite population. So now the last thing here, if we have n, which is the sample size, divided by the population size, so sample size divided by population size greater than 0.05, then we have to use a correction value when we calculate sigma x bar. So now let me write it here. N divided by n less than 0.05, then sigma x bar equal to sigma divided by square root of n. But if we have n divided by n greater than 0.0, so this is equal to 0.5, then sigma x bar will be equal to sigma divided by square root n times this value, which is, so remember that n capital is population size and n small is sample size. Okay, so that's it for this session. Good luck.